Okay. Yay, good work. Thanks for your patience, Ben. So Ben is manager and co-lead for the large behavior model project at TRI. Before joining TRI, Ben was postdoc at Brown University and a PhD student at Duke University in the Intelligent Robot Lab. He worked on 3D perception, learning from demonstration, and multimodal vision language representations. Today, he will be giving a talk on large behavior models. Thanks again for joining us. Take it away.
Yeah, absolutely. Great to be here. Like Sasha said, these days I'm co-leading TRI's essentially embodied foundation model effort. And so that is basically our push to make general purpose robots essentially powered by sort of image in, machine learning model, action out paradigms. And there's kind of an opinionated stance that I think has been increasingly loud in some parts of the community over the last year. I think for people who are at Coral, this was one of the big themes there, and that is that maybe scale is all you need. And there was actually a very nice panel at Coral where people sort of debated this back and forth. And do we need more algorithmic innovation, or maybe we can just take existing approaches, use more data, more compute, and essentially solve robotics? And my opinionated stance is that this is probably not the right question. And actually, nobody knows if scale is all that we need. But what we do know is that we need scale. And to the extent that we're going to need new algorithms and new paradigms, it isn't obvious what the limitations of current methods are unless we push them. And it's also, I think, very difficult right now to kind of engineer your way to better robots if you ignore machine learning, you ignore scale, because it's very easy to do something and then in 6 months, it turns out that the structure that you worked very hard on inducing in the problem, it just kind of emerged naturally from larger scale training. And that's really the stance that we take at TRI, which is that we are doing machine learning at enough scale to see where the limitations are and then push in the right places algorithmically. And the goal of these efforts really is to build essentially a model for robot behavior. So sensor data in, actions out, that starts to exhibit things like sort of large language model style generalization. So what we would like for these models to show is to be able to learn from one example or potentially 0 examples. If you ask your robot to do something that's fairly common, hopefully it can do a reasonable job without any new teaching. And we'd also really like some emergent common sense style behavior. So these could be things like principles, such as, don't get into the personal space of a person, don't knock things off the table unless you're specifically asked to. And also things like compositional robustness. So if you know how to manipulate a particular type of object, can you use similar motions and similar strategies on new things you haven't seen before? Or can you compose 2 strategies from 2 different behaviors to do something novel? We want to see that sort of generalization. And we also really want to see generalization across devices. So this is something that isn't as much of a factor, say, in the LLM world, where there are a relatively compact set of languages in the world. I mean, compact all being relative, but several hundred languages in the world, each with a decent amount of training data. When you compare that to the amount of hardware diversity that we have on robots, where most people have kind of their own bespoke setup still, there's an additional challenge of learning something that actually works across diverse hardware. And so the sort of mental model that we and a lot of other groups are pushing towards is asking a robot to do something and it just kind of works. So you can give your robot a natural language prompt and have a reasonable expectation that it does something that, if maybe not perfect, isn't kind of catastrophically bad. And like I said before, the way that we are looking at doing this right now is essentially training models that take sensor data and instructions and predicting robot actions. And it's going to be a while, I think, before we have what we're calling large behavior models. So these are models that exhibit some of those general properties I talked about. But that's okay. And in the meantime, I think a lot of the push is to show sort of proof of life. So are we in the sort of general regime where we start to see any of this emergent behavior, or are we a few orders of magnitude off in terms of data scale? And I think getting a better sense of that and starting to understand the relevant scaling laws is the big push for a lot of organizations over the next year or two. And really it's, what kind of resourcing do we need? Could we build something that's like the sort of GPT-1 of robotics, GPT-2 of robotics, and then make predictions about what it would take to get to something actually useful, like a GPT-3 or GPT-4 style model? So a little bit about us. We are split between 2 locations in both California and Cambridge. And so most of our group is actually housed out of the Cambridge lab. This is a drone fly-through from about 6 months ago of the state of the lab back then. You can see we have a large number of fixed manipulation stations that we're working on these days. Pretty much all of them are bimanual. We've come to realize that that's pretty important just in terms of enabling diversity. Turns out that you can do a lot more with 2 arms, even when your grippers are relatively simple than you would think. But as soon as you have 1 arm and you can't really do object reorientation without setting it down, it just becomes actually pretty quickly that a person looking to teach a robot kind of runs into the limitations of hardware. And so when I say we're doing behavior learning from demonstration, what I mean is that we generally have human experts that teleop robots through behaviors that we'd like to teach them. We have a few different teleop interfaces that we use. This is probably my favorite. So this is a haptic-enabled teleop device. So it closes the loop between the forces that the robot is sensing and the operator. And you can actually do pretty dexterous things with this. So this is my colleague, Eric Cosino. And this is a teaching demonstration that he's teleoping here, showing how you can use an egg beater with our bimanual robots. And so from a set of these demonstrations, generally on the order of 50 to low hundreds, you get learned behaviors that look something like this. And so this is an autonomous policy rolling out the end result of about 150 of the sorts of demonstrations you saw in the previous clip. So a little bit more about our setup. A little bit more about our setup. So we have a fleet of over a dozen of these bimanual stations. We're currently using 7DA Franka Panda arms. And the thing that we really like about these is the force sensing is pretty good. So like you saw with that haptic-enabled device, being able to feed forces back from the robot lets you do some pretty cool things. And in particular, that example with the egg beater, actually, if we turn off that feedback loop with force, humans have a lot of trouble doing it. The handle that you hold actually can come off. It can like pop off of the shaft that it's attached to. And if you can't feel the amount of force that you're applying, essentially, 50% of the time you go to demonstrate, you sort of rip the thing apart. So it's important actually to have a robot that has relatively clean torque sensing so that you can do that sort of thing. And the other thing that you can see in this setup is we try to put our human operators pretty close to the robots. And one of the things that we've found is pretty useful while you're doing both demonstration and evaluation is being able to perturb the scene. I'll talk a little bit more about robustness and why that's important, but having people that can physically interact with the robots during both demonstration and autonomous rollout is also very useful. So just to give you a little bit of a better sense of what these sorts of demonstrations look like, here are some of the recent ones that we've been collecting, and you have a view here which is both an external scene camera and also the wrist cameras. And we found that actually having wrist cameras included when we collect training data is pretty important. And in particular, it seems to actually help a lot with generalization. You can see that the field of view on the wrist cameras are relatively small. And over the course of a trajectory, the viewpoint's actually changing pretty dramatically. And that seems to be an important, almost like a type of domain randomization that makes these policies more robust in many cases. We also sometimes use non-visual sensing. So this is a view from a tactile enabled sensor that we use on some of our robots. It's a little bit like a gel sight, for those of you familiar with those. In this case, this is a camera that is mounted behind a membrane that's been inflated with air. And so on the rear of that membrane, essentially bubble, there's this textured pattern that the camera can observe. There's also a light source in there. And so we can essentially use the image from that camera just like any other sensor input, but now it's measuring the force and shear force and deformation of this membrane, and essentially giving us a tactile sensor. So the one being shown here is, let me skip ahead, there we go. So the one being shown here is on that robot's left arm holding the cap, and you can see, as the cap is coming into contact with things in the world, it's deforming. And so you get a really nice sense of the forces that you're applying, and in particular the shear forces, which can be pretty critical for some applications. I'll skip over this a little bit. Let me know if any of you have questions about the hardware setup. We actually do have RGBD sensors on the robots, and we occasionally use depth for various pre-processing or augmentation steps, but we don't actually directly condition the policy on anything other than just the RGB signals. And just a few examples of other haptic devices we use. This is, or other teleop devices we use. This is non-exhaustive. In addition to these haptic devices on either side of the image, we use a 6 degree of freedom. We call it a space mouse. These are kind of made for graphic design. For very simple skills, these are also fairly nice. We found foot pedals to be pretty useful for discrete input. You can do things like commanding the robot to move to a pre-programmed set point, which is especially convenient, say, if you're resetting the scene. And recently, we've also been doing a fair amount of VR-style teleop as well. The other thing that we lean on fairly heavily internally is simulation. So in addition to real-world data, we are one of the main developers of the Drake simulator. And so we have a team that works pretty hard to ensure that there's a relatively faithful recreation of our robot stations in simulation, so that we can generate some of our data without needing real-world rollouts. And so this is the sort of standard Drake simulation and Drake render on the right. The thing that's pretty neat is Drake supports flexible rendering. So if we want to, we can take some of our simulation data and we can use really high quality rendering. So on the right, this is that same trajectory rendered with Blender. And if we push on it, we can get things that are really like almost photorealistic. So I'll talk a little bit about how we use this to learn individual skills. In the second part of the talk, I'll talk about going beyond that and kind of how you go from reliably teaching individual behaviors to sort of this general purpose paradigm. But the last year has actually been really exciting just from the standpoint of you'd like your robot to do something interesting. Can you make that happen? And essentially, I would say basically we're at a 10 to 100x speed up in getting simple behaviors to work with this paradigm. So, for fun, we've been recreating some of the behaviors that we did, 3 years ago with very structured approaches, and things that used to take us a month, often we've been doing in just a day, kind of work the first time for fun. And the setup for making this happen is relatively simple. So what we use internally is a supervised method called diffusion policy. This is basically just using a diffusion model as the generative model that produces your outputs. And so this is conditional diffusion, and in much the same way that an image diffusion model conditions on a language prompt and then gives you an image, we condition on the robot's sensor observations at a particular time step. And then we diffuse random noise into actions, and we basically put this in a loop. So we put this in something like a 10 hertz control loop. We predict a trajectory or sequence of actions into the future, and then we execute the first part of that predicted trajectory until 100 milliseconds have gone by, we replan, and then we start executing that newly predicted trajectory instead.
Sorry, yeah. I think there's a question in the chat regarding the use of proprioception.
Yes.
That's from me, actually. I think I heard you say that you used only RGB data to feed into your policy. And yet, 2 minutes earlier, I heard you talk about how good the force torque sensing was on the Franca and like how useful it was. So why not use it?
Yeah, sorry, we do use proprioception. Okay. I should be more clear. We use RGB only as opposed to using depth. So from our image sensors, we only use RGB. We actually generally condition on proprioception, usually in end effector space. RGB from all of our cameras, and I'll talk about a little bit later on, also a prompt or a goal or a language command as well. Proprioception is a little bit of a black art still. It often helps. It sometimes seems like including proprioception can make policies more brittle. And there isn't really consensus in the field about what form that proprioception should take. So both in terms of how long should the observation history be and whether you want to do proprioception, say, in joint space or in task space. Usually what we'll do is we'll do about a second of proprioception in task space. But again, it's not, I think, a completely settled matter about exactly where it makes sense.
Okay, thanks a lot.
Yep.
Maybe while we're discussing perception, other labs, I know some other works where they really kind of bake in 3D perception in their manipulation pipeline, right? So they diffuse specifically over the 3D scene, or they use point cloud, voxels, that kind of stuff. So what's your take on this? Why did you guys choose to only use RGB and not use depth or dedicated kind of 3D representations?
Yeah, so full disclosure, we've used some of these techniques internally, and I think right now they can be very convenient. One of the big failure modes, especially if you teach one skill at a time, is like viewpoint brittleness. You move the camera and performance degrades, or the policy breaks completely. What we've also seen, though, is that as you start using more powerful, just general pre-trained models, not even particularly 3D ones, and especially as you start training policies that are multitask, so trained to do multiple things at once, robustness to viewpoint change seems to be one of the first things that emerges. It's my personal belief that a lot of these kinds of basic structures that we would think to bake in are actually the ones that will emerge most quickly from just training with more data at scale, and specifically co-training with things like video and image generative models. And the reason for that is really, a lot of times when people think, what inductive bias do I want to bake in, you think about something that's basically universally true. And so like 3D geometry is true always, like that's how the world works. But if something is always true and it's present in basically all of the data you feed through, that's usually a relatively simple thing to learn. And the challenging parts are often some of the edge cases and some of the more subtle bits. But the problem there is those edge cases are very hard to kind of model succinctly and explicitly in a way that doesn't kind of limit the power of the policy. And so I think, in the short term, there's a lot of room for this kind of explicit structure and bias. I do think over time, we're going to see people kind of moving away from that. And it just, I think, won't necessarily give you much over training at a bit more scale.
Okay, thank you.
Yep. So there's a few architectures that we use. The most basic one actually is just a set of encoders. We've used both transformer or ResNet encoders for these. We haven't found a significant difference between having one encoder kind of per image modality, so like a wrist camera encoder or a scene camera encoder, versus a larger joint encoder, just for the sake of showing a representative version. One thing that you might have is, say, a set of 3 ResNet 18 encoders, one for tactile, one for wrist cameras, and one for scene cameras. Those produce a feature vector, and then we do something like film conditioning, usually to condition our denoising head on the features extracted from the sensors. And before we do that conditioning, we concatenate any other low-dimensional signals we condition on. So this is where proprioception or language embedding or other information like that we want to condition on gets included before the denoising head. Usually we do something like 8 time steps executed before we replan, and we found it's pretty important to predict a longer tape of actions than what we actually execute. 16 and 32 are both pretty common choices. Things don't tend to be too sensitive to this parameter, but there's a big difference between predicting, one action at a time versus a longer sequence, and longer sequences definitely help. So I just have a few examples of some things that we've done recently using this setup. This was one of my favorites, just because it's highly deformable and would have been a giant pain with a more sort of structured model-based approach like we were using a couple of years ago. I think this is one of the canonical examples when I think about, all right, what did we do in a day or two that would have been just a heavy lift pretty recently. The other thing that I like about this task, and you'll see in a second, is it was actually trained to be ambidextrous. So here now the mat is rolled the other direction, and the robot is able to essentially switch which arm it's using for what to unroll it. And there's no magic here. I mean, the reason it can do this is that in the training data, we demonstrated doing it multiple ways. So this isn't emergent. It didn't kind of come up with it on its own, but this approach is flexible enough that you can build this sort of robustness into the skills if you're careful while you teach them. And this is just kind of a high-level overview of some of the variation that's pretty exciting about this line of work. So again, because you don't have to model anything explicitly, whether you're dealing with deformable objects or thin objects like pages of a book, or liquids like sauce, or in the lower right-hand corner, you can see we're peeling vegetables. So there's sort of physical property changes that are happening. You don't need to make any specific modeling decisions. Whereas previously, if you have to kind of design a perceptual representation for each of these different situations, it really is sort of a separate effort when you want to do something new like that. And then this is another one that I really like, because it was essentially impossible without the tactile sensor on the finger. And so what's happening here is we're going to pick up a bottle cap, and the task is really just tighten the bottle cap on this jar. And we filled it with marbles. At the end, you'll see the robot sort of picks it up, and what that does really is just make it very obvious if you've actually tightened the thing on properly, because if not, you're going to dump marbles everywhere. And the tricky bit about this is that visually, there's very little indication of how tight that cap is. I mean, maybe if you look very closely, you can sort of see what the gap between the cap and that ring below is. But remember, these images are downsampled, and there's a pretty small visual difference between tight and not tight. And we couldn't get this skill to work without a tactile sensor. And with the finger, it actually is quite easy. And the thing that's neat is you can see as my colleague perturbs it here, the robot will sort of keep tightening. And that'll keep going until at the end here, you can see it's starting to have to apply more force. And as far as we can tell, it's cueing really very strongly off of that shear force that it's implicitly able to observe. And then this was just trained as a single end-to-end, somewhat long horizon skill. So it's just mode switching kind of implicitly because of the training data. And I think we've once kind of sat there for like 10 minutes. You can poke at it and mess with the cap kind of indefinitely, and it will just keep on trying to tighten until it feels it is snug. So this is exciting, and I think we've seen a lot of really, I think, impressive behavior learning in the past year from a bunch of different groups and methods like ACT, diffusion policy, the RT line of work. But I also just want to kind of emphasize how different this is than 2 years ago. It's easy now to sort of say, well, it's supervised learning. It's really simple. You throw data at it and it works. And that's true. But this is also really a new thing. And so now we kind of have this powerful building block that we can use that even just a couple of years ago didn't exist. But the other thing to keep in mind is that a lot of these sort of impressive looking behaviors that are being shown, including the ones that I showed, they're not magic. And in fact, getting one behavior at a time to work well is kind of more of an art. There's a lot of data quality that's involved. There's a lot of care when you're teaching. And you really have to think about your data coverage of what matters. So what variation of background do you expect? You should try to include some of that in your training data. What sorts of interactions, like with the world, do you need to cover? Are there recovery behaviors that you want the robot to have? If so, you better have those demonstrated in the training data. And so really, it becomes quite expensive when you're training one skill at a time to make it robust, because you have to anticipate all of the edge cases that you care about. And for a real world robot, there's a huge number of those. And there's some things like Dagger, or having a little bit of kind of care and consistency with how you solve problems when you're teaching that can help. But ultimately, it's still something where the teaching strategy matters a lot, and there's still a lot of art involved. And so here's kind of an example of that process. So this is like the very first version of that egg beating behavior that we ever taught. This was actually fairly early last fall. So we just started getting into teaching more complicated skills. We weren't as good at it yet internally. And so with a somewhat kind of naive, half-baked attempt, we get a policy like this, where it's really hesitating quite a lot. And then some of the time it kind of works, and then you can see it sort of falling apart. And what happened here is a mixture of things. So one, we weren't very consistent in the demonstrations, and we didn't have very much data. This was like the first 50 demonstrations. And so you can see the policy is trying to kind of switch modes. That's part of the reason it's so jerky. And the other thing that we weren't careful enough about is once we got the egg beater in the bowl, the human demonstrator had this kind of consistent drift. And in practice, the human didn't sort of always drift all the way off to the side and fail, but it was present in enough of the data that it basically biased the robot to just constantly move right. And so you can see the behavior just sort of deterministically moves right until you hit the edge of the bowl and fail. But yeah, looks like we have a question, Liam.
Hi, yeah, thanks. So, it's interesting you showed this example because I'm not I guess I haven't looked in detail at the action diffusion, that you're using here, but it would strike me that there is some possibility that if there is multiple modes, that you could get, since you're just sampling at every time step, this diffusion policy is just sort of like sampling from basically the action distribution, that you could get this possibility of like thrashing between modes, which I think is kind of what you're showing here. And so I was gonna ask this question already, but now you're giving this an example. So like, is this to what degree is this actually like a fundamental limitation of the diffusion policy? In particular, if there was like a task where there really was multiple ways to do it and you had demonstrations that the demonstrations really were multimodal.
Yeah. So yeah, that's a great point. And there's kind of a subtle double-edged sword at play here. So diffusion, like a few other methods that are able to model a multimodal distribution, theoretically, it's quite nice in that it can represent multiple modes in your training data. However, the reason that's kind of a double-edged sword, like you said, is that if it is not clear based on your observations what mode you're in at any point in time, that can also result in this sort of thrashing. So with older kind of direct, like mean squared error supervisory approaches, if you have multiple modes, you sort of average between them and often end up doing something bad from the get-go. With models that have mode collapse, that isn't necessarily an issue. You just pick a mode, but the problem there is that if something perturbs you and you actually end up in a different mode, often you are out of distribution and don't perform well. So it's nice in theory to model these modes, but really what you need to do is you need to make sure that with the observations you're conditioning on, there's a clear mode that you've committed to. And right now, the observation histories that we use for these things are fairly short. The robot only has like a second of history. And so that's making you more sensitive to switching modes. I think one of the big solutions will be stretching that history to much longer horizons. And when we get to the point where your entire rollout so far is in your observation history or in your context, I think it's going to be much more apparent sort of what mode you've committed to. And instantaneously, if you imagine there's maybe two ways to go around an obstacle, sure, you could go left or right. But if you look over time, if you're jittering back and forth, that is actually not in a dense part of your training distribution. And so I think that's kind of the thing that will save us. However, doing that takes more data. And so what we've also seen is that if you just naively increase the length of your observation history and you have, so let's say, only 50 training examples, you just overfit really severely. And basically you get a policy that's so brittle, it's like only playing back a trajectory. So I think some of these things are just going to get better with more data and longer observation histories.
Great, thanks. That really, really clearly answers the question. Thanks so much.
Okay, let's see. I want to just keep an eye on time here. So I'm going to skip. I had a few examples of sort of iteratively getting better. I'm going to skip one of the intermediate ones and instead show this. So after a couple of iterations of training data, we now get a skill that's starting to have a little bit more reliability. And it's actually a little bit reactive now on the right to like where we put that beater, because we've trained it with things in multiple positions. But this behavior is now really sensitive to where that handle is. And that's just because when we actually were resetting the scene, the demonstrator kind of carelessly always put the handle in the lower position. And if you're teaching a person, of course, that wouldn't matter. But this is, again, one of those examples where really think about the distribution of initial conditions you want. And so if you go back, and essentially this is now the same data as before, but we added another like 80 demonstrations with just more randomization. So we randomized where the bowl is, and we showed a few examples of pushing it into place if it's too far over. We randomized the initial condition of the handle of that beater, in addition to randomizing the location of the thing that's holding the beater. You can kind of brute force robustness, and you can see, now that you have a policy that will sort of chase things in the scene as they move. And again, it's great, but you don't get this stuff automatically or for free when you're teaching one behavior at a time. It's kind of encoded through blood, sweat, and tears. I want to show you another example of something very ambitious that we did. If this video will load for me. Okay, well, we can skip this example, but I think the main takeaway I want to give you all is that when you're teaching one behavior at a time, it's tricky and performance isn't free. And there's a lot of domain expertise that goes into it. And again, just to keep us on track here, I'll skip over that one. But that doesn't mean that you can't get some generalization. It's just that when you do, it's often kind of an accident. So there's a funny case where on the left, we trained it to peel potatoes. We had like 100 different potatoes. And if you have something that looks mostly like a potato, but isn't exactly, sweet potatoes were no problem. And then funnily enough, we found the same policy seemed to have just kind of fit to, if you see an object in the gripper that's roughly, several inches long, make contact and start peeling. And so that policy kind of happened to work on a carrot. But again, this sort of thing is more luck. And for every time that you get a policy that has this sort of generalization, you get another policy that's like head-scratchingly brittle. Okay, there's a shadow across the world, and now performance has degraded, and maybe I should go back and either increase the amount of domain randomization in my training pipeline or, close the window. We've gotten a little better at this though. And so we're at the point where pretty reliably, if we can teleop something, and I would say if we can teleop something that takes like less than a minute to do, we can almost always get a decent policy. So this is a recent one that we did, basically folding shirts. And this was kind of near and dear to me because we actually had a collaborative effort 2 years ago where we spent a semester getting a robot to fold shirts. And in like 2 days, I think this was a better folding job than we got in several months before. And here, kind of learning from the things that we showed before, we sort of knew ahead of time, all right, we want to randomize initial positions a lot. We want the shirt to sometimes be crumpled. We want it to sometimes have like a fold when one of the steps completes. So we occasionally reached in and perturbed it to force the robot to learn some sort of local recovery behaviors. And if you know these kinds of tricks, it makes it a lot easier. So I won't harp on this too much, but I think the short version is that learning from demonstration is real now. If you want to get a robot to do a simple thing in a controlled environment, supervised learning works really well, and you can pretty reliably get the robot to do what you'd like. And so this is exciting because we have a generic recipe now for decent kind of narrow skills. And it's a little bit more clear kind of what the limiting factor is, which is really reliability and generalization. And I think there's an obvious answer there, which is we want to scale the amount of training data that we use. But unlike other domains like language, where there are large existing data sets, and when you want to scale, it's basically a matter of pulling those data sets in, there's the question of, okay, well, how should we scale? So you have a particular amount of resources, and you say, all right, well, let's go out and we'll collect more robot data. And now because you're collecting the data, you have to kind of choose what to focus on. Do you want to go for quality? Do you want to go for quantity? So maybe your demonstrators aren't very careful, but they can demonstrate much more quickly and you get more samples. Or do you really maybe want to focus on diversity? And you could go out into the world, get out of the lab, and get much more diverse data. But again, it's sort of at the expense of data quality. And so it's really a balancing act of these three factors. And I think we're at a place where people have a lot of intuition and kind of fuzzy inklings of what they like. I'm personally in the diversity camp. I think that's like one of the critically important factors. But quantifying exactly the trade-off between these things and how that impacts scaling performance will be one of the big next steps for the field. And kind of standing in the way of this is that benchmarking remains a pretty serious challenge. Hardware experiments are difficult. Simulation, I think, is a promising tool there, but performance in simulation doesn't always correlate to performance in the real world. And offline evaluation has been essentially useless for us. So offline validation sets and looking at offline metrics really haven't told us much about what online performance of these policies will be. And so I think, there's a lot of room for theoretical contribution. I'm pretty convinced that we have not reached the sort of perfect formulation. But I think in order to figure out what theoretical contributions are useful, we need to get a lot better at benchmarking and evaluation. And the other thing is we need to study this, I think, in the context of larger scale learning problems, so that some of the brittleness I was just talking about doesn't kind of get in the way of seeing signal. There's only so much you can do with 100 data points. And that kind of brings me to the next section here, which is on learning multitask models. And this, I think, is really the direction everybody is going. So now, instead of teaching one behavior at a time, you're going to teach multiples. And a common way to do this, and the way that we approach this, is to augment our observation encoder with a language encoder. And so now we're conditioning not only on what the robot sees, but also with a task prompt. And often this is something simple, stack the bowls, load the dishwasher, flip the pancakes. But there's some tricks that we play usually, which is that we feed these prompts through an LLM and we request it to basically augment. So, we'll prompt engineer, like, here is a prompt that we're giving to, someone who's helping us around the house. Please rephrase this in 100 different ways, those sorts of prompts. And we find this makes the resulting policies a lot less brittle, obviously, to the phrasing that you use. And so then you just approach the learning problem in the same way that you do in the single skill case. It's just now that your training data is a shuffled mix of data points from multiple skills instead of one. And even at the fairly small scale, this has been a pretty powerful change. So on the left, this is an example of a really basic single arm skill where you stack the bowls. And in this case, I think someone had headbutted one of our scene cameras inadvertently. Like I said, the camera movement is a very easy way to break these policies that are learned on one skill at a time. Again, there's been some exciting work in the past year or two, I think, on 3D representations designed specifically to address this. But we didn't do any of that in this case. Instead, we just taught 15 skills at the same time, didn't change anything else, didn't change the visual representation. And that was enough to give us some viewpoint robustness, and in this case, to basically repair the behavior. Again, it doesn't suddenly make your behavior perfect, but it unbreaks it. And this, again, is part of the reason why I think, while inductive bias is useful, and it may kind of help us jump forward along the x-axis of scaling, I do think that over time, the need for some of this explicit structure is going to diminish. And here's another example. This one's a little bit more dramatic. So we've trained a behavior which just pours ice in this mug into a sink. Here's a training example. And the world's really clean in this case, like there's no visual distractors. And so if you fill the world with a bunch of stuff that's never been seen before, the single task policy essentially goes horribly out of distribution, and in fact, the robot needs to be e-stopped. And this is a multitask policy that was trained on several dozen skills. And again, without changing anything else, just mixing different behaviors, we've ended up learning robustness to some of these visual distractors. And I think you could probably do a similar thing with explicit structure, like introducing objectness priors or conditioning on object detection. But in this case, you see that just kind of scaling the learning problem seems to give you some of those same simple sorts of robustness kind of inherently. And there's some more subtle things that change as well. We find that motions tend to be a bit more purposeful. Ignore the fact that the single task policy is kind of missing in this case. I'll talk about that in a second. But just the if you ignore what the task is and you kind of look at, does this reasonably fall in the marginal distribution of behavior? We seem to get more natural motions when we go to multitask. And the policies also tend to be less likely to go open loop. One of the failure modes that we see in the single task case is you'll have a phase of your rollout that's just pretty reactive to the environment. And then you'll have a phase where you're essentially, the policy is sort of switched into open loop execution. And so here you can see that's obviously the case because we've misgrasped the mug and the policy is kind of continuing on towards the sink on the left like nothing has happened. But even this, this multitask paradigm, these aren't large behavior models. And I think it's exciting, maybe not totally surprising, but it's exciting that training on multiple behaviors at once seems to be a really powerful technique for representation learning that doesn't get you to emergent behavior. And I think to do that, there isn't really any way around it. We need a lot more data. And in particular, I think, we should scale the robot data. That's great. And in fact, that's what we're doing internally. But that's not going to get us there either. We need a lot more data than anybody can conceivably collect in the next couple of years. And so really the big bet here needs to be on transfer learning. Can we get enough robot data that we get alignment with other sources of non-embodied data that doesn't have action labels, and get a lot of our kind of emergent capabilities from those other sources? So yes, I think as a field, we should be making public as much of our data as we can. We should be sharing it. We should be training on it. We should be using simulation and high quality, privileged planning and control methods so that you don't need to teleop in simulation to scale that source of data. But we're also going to need to be reaching for other data sets. And in particular, I'm really excited about both VQA style data and also video. I think video and video generative models have a ton of potential to play a big role here. And essentially, I think the first large behavior models that we'll see will be getting a lot of their horsepower from those other sources of data. And hopefully the robot data is enough to ground that and align it into a robot's action space. And there's one other sort of detail that I want to share here in the last couple of minutes in the direction of scaling to the extent that I think we need to. And that is removing some of the bottleneck for the embodied data on teleop, where it's just hard, especially if you want diverse data in the wild. You need to deploy your robot. You need to train a person to teleop through the robot, which is not generally super intuitive. And you can put people in VR headsets, which is also great, but how long do you really want to stay in a VR headset? And there's just a lot of sort of difficulty and learning curve that slows down the process. So we had, I think, a really exciting intern project this summer. Chung-Chi, who's one of our collaborators from Stanford, he came to us and had this idea of basically, hey, instead of having to deploy a robot in the wild always, what if we use a handheld setup to collect data? And there've been a few people who've done this before. I think the kind of key insight here is let's make it as simple and low cost as possible. And so he spent a lot of, I think, really important and impressive engineering time just removing complexity from the system. So we have a 3D printed setup that just uses a standard GoPro to capture data. So you get RGB and IMU data without needing to do any other online processing. And then we post-process basically using OrbSlam 3 in order to actually get trajectories through space. And there's a little bit of other engineering detail that I won't go into here that you need to do to kind of put that data in a format that works well for robots. There's some timing issues and sort of other aspects. But when you put it all together, you get something that costs only a couple $100. And sorry, this video of him is slightly sped up here, but you get something that costs only a couple $100 and is really natural for a person to use. You can, pull it out of your tote bag, pick it up, and just kind of start, interacting with the world like you're using, one of those children's toys. And this particular example, actually, was one of my, I think, favorite results from the work, in so much as we used it to teach something that was pretty long horizon. So we had a set of, I think it was around 150 demonstrations like you just saw. And the end result is a policy that works out of the box on the robot. And in this case, part of the reason that we're able to do that so directly is we put the same camera on the wrist of the robot. And from the robot's perspective, while the gripper looks a little different, the fingers are basically the same. So we're able to keep the embodiment gap really, really small. And I think even as things like hand tracking and some of these other methods that let a person without any unique tools interact with the world, the advantage of this method is that it constrains the person's action space. So you can't accidentally do things that requires in-hand manipulation if you have a parallel gripper on your robot. And so it sort of forces you to choose behavior modes that are going to transfer well. The other example that we use this for, which was quite nice, was cloth folding. One of the tricky parts of folding cloth with teleop is it's a very thin structure to grab. And while people are learning to do it, you'll actually see that they often kind of miss because you need to line up very exactly. And it was just really, really easy and natural for a person to do this with these devices. So this was kind of the twin version of what I showed before. But while that behavior took a little bit of trial and error to get right with teleop, with this one, it was essentially, we just did it and it was fine the first time.
Are those policies only using the wrist cameras, or do they also have like a third-person view of what's going on?
These ones are just using the wrist cameras. So we kept the embodiment gap, as small as possible in this one.
Okay.
Yeah, so I mean, that's essentially where things are today. And I think there's a lot of open questions about what comes next and where things are going. I think there's kind of three critical ones that I've been thinking a lot about. Probably the biggest of these is supervision sources and what makes sense beyond robot data. My personal bet, like I said, are video models and language supervision. If I had to just pick two, those are probably my favorites. But there's a whole landscape of things out there. And I think also I want to call out some of the more structured approaches, be they object-centric or explicit 3D, instead of being used as the sort of architectural decision, like in your architecture, they could also be recast as an auxiliary supervision source, which has the advantage of letting them kind of fall away in edge cases where they could be limiting. And so I think there's a really big, fairly open design space there to be explored. Another one is how do we get something like online adaptation or in-context learning? I think the field is still somewhat divided about this. There's a camp that still is betting on like explicit RL being the thing. I'm not sure. If I had to pick, I would say probably we want something that looks more like explicit in-context learning. And how do we get enough data to make that happen? I think is an open question. Another one is, are there specific types of supervision that we can give that allow in-context learning to emerge sooner than it would just naturally, like it did in the language setting? And the final one, like I alluded to before, are just data diversity trade-offs. Data is still expensive. It's going to be expensive for the foreseeable future. And so how should we as a community think about allocating our limited resources? What sorts of data is the most valuable? And with that, I just want to call out, the entire team. Efforts like this have a lot of moving parts and really are only possible when you have a really diverse cross-functional set of people working on it. And all of the work that I talked about today is the result of many different people's efforts and hard work and creativity. So that's all I have. And I think we're somewhat close to time, although I could stick around for a couple extra minutes, if there's sort of more discussion, but I'd love to take any questions.
Wonderful. Thank you, Ben. Thank you. Okay. Any question for Ben? Oh, I think we have Liam.
I had a couple of questions. So maybe just to start with the specific question. So like in the example that you just showed, where the guy kept putting the ketchup back onto the plate, that's able to react to that situation like purely because it's in this like NPC framework where it's constantly replanning. That's the mechanism that's being used to get that robustness, right? If I understand correctly.
So there's two mechanisms. So that's one. You need to be basically replanning in a loop. It's not exactly NPC. It's just that you are kind of constantly replanning. The other mechanism at play there is we had basically one of the other authors on the paper was kind of out of frame and was squirting more ketchup on the plate sometimes, even while he was collecting training data. So again, that one is not an emergent example. That's like we taught it explicitly to be reactive to that sort of perturbation.
It's possible that this could happen, yeah. So, okay, so given that, And then in the context of what I asked previously, where you sort of were alluding to the fact that like to overcome multimodality, maybe one of the tools in the tool belt is to just increase the length of the horizon. I'm just curious about the like real-time performance of
Yeah.
actually running the diffusion policy inside of
Yep.
this loop.
So I would say the inference budget that you have is definitely sort of a critical constraint. And internally, I think we definitely spend a fair amount of effort making sure that we stay within our inference budget. The good news is that there's a bunch of techniques to pull from, and some of them are pretty simple kind of engineering style techniques. Whether it's JIT compiling your models, whether it's looking at architectures that are kind of like flop optimized. So for a given model capacity, what is the highest throughput that you can get for that capacity? And then, there's sort of a spectrum. So we've started looking at model distillation. Of course, you can quantize these things as well. The other knob, especially for diffusion, that's pretty impactful are the number of denoising iterations you use. And there's a few different ways that we've been able to get the number of iterations down. One is using an implicit formulation, which it's DDIM. For those of you that aren't familiar with it, in practice, if you're implementing diffusion, it's definitely what I would recommend. And it lets you change the number of denoising iterations between training and inference. So your number of inference iterations can be smaller. And we're looking at second order optimization methods to maybe reduce the number of inference steps further. And then there's even more kind of, I would say, structural changes like hierarchical policies or policies that have sort of multiple components that run at different rates. I think there's a lot of games that can be played, but it's definitely an important factor when you're deciding what kind of model can I use for this.
And maybe thank you, that's great. And maybe if I could ask just one quick follow-up. So am I correct in assuming that there is this kind of like trade-off between the action history and the inference time? Like, to what degree does that action history impact the inference time? Is that a key contributing factor?
Yes, it is. I think right now, just given the exact networks that we're working with, the biggest limitation is actually the size of the denoising head and the number of denoising iterations, because that essentially runs in a loop. Right now, the encoder cost doesn't dominate our inference budget. And part of the reason for that is that we haven't needed enormous encoders because we don't yet have enough data to make that action history larger. And so I think it's mostly where the bottleneck is. I expect as we get more data, we start using larger encoders, you're going to see that balance shift and it's going to become more of a problem.
Okay, super. Thanks so much.
Okay. I wonder what you think. Like, do you think that the current approach will transfer well to the mobile manipulation setting? Because all the results we're seeing are generally tabletop.
Yeah.
And I guess in the mobile setting, like the history you have, like the history will matter a lot more because you might need to navigate multiple rooms, that kind of stuff. So yeah, do you think it will transfer well, or where do you think that things will break down?
Yes, I think the short version is I do think it will transfer well. We've had a few work in that direction. I think Mobile Aloha, although the hardware experiments weren't super extensive, was also a really promising sign. They had just very, very simple formulations of basically predicting, velocity with a direction for the mobile base. They folded it into their action space, and they basically didn't change anything else about the problem structure, and were able to get their system working pretty well. I would probably even go a step farther and say that I think mobile manipulation is going to be key to getting general purpose policies. I think having a significant variation in sort of viewpoint and perspective on the world, and also encountering cases, where an object is just out of reach, and you either need to compensate with your manipulation strategy or move your body. It's easy to be in a binary situation with a fixed setting where something's either possible or it just like isn't. And I think in the mobile setting, there's a lot more room for sort of creativity and improvisation. And as we want to get these models that really have enough of a challenge from their supervision, to have like emergent properties and some of this creativity and robustness happening more organically, like without a person explicitly teaching every version. I think mobile is one of our best tools to getting that to happen.
Great, thank you. Any other questions? Don't think so. Okay, I think we can call it. Thanks again, Ben. That was a wonderful talk.
Awesome.
Thanks
Well,
so
thank you all
much.
so much. Yeah, thank you so much for having me. This was a lot of fun.
Thank you. That was great.
Okay, thank you.